Hey, AP Chemsters, this is Mrs. Vanderwall bringing you the 15.6 Part 2 edition of Blankwalle. So we are now talking about how to work the ice tables for these acids and bases, well, mostly acids right now. And we saw earlier how we would use the ice tables in a way if we have a strong acid, which, as you remember, is 100% dissociation. But what do we do if we have a weak acid, and where the Ka is usually, not always, but usually a very small number, like 10 to the negative fifth? What do you remember about 10 to the negative fifth? That's when you can use your X is small approximation, and that's where I taught you the German phrase "Ich bin sehr fröhlich," all right, where that means I am very happy. It's a lot less work if you can do this without using the quadratic equation. So the steps that they list here are the identical steps that we did in chapter 14, where we go through, we set up the ice table, we decide, what is X, what is, minus X, and what we can cancel out. So the same rules apply. It says list the major species in the solution, choose a species that will produce the H plus, and write the balanced equation. Make sure you can do that. That's where you have to know the acid and the conjugate base. Using the values of the equilibrium constants for the reactions you have written, decide which equilibrium will dominate producing the H+, meaning will it be water or will it be the acid? Write the equilibrium expression for the dominant equilibrium, list the initial concentrations, define the change, write out the equilibrium concentrations in terms of X, so that's the E section of the ice table, substitute them, solve for X the easy way. Make sure you do number 10, by the way, so use the 5% rule, and then calculate the H plus and the pH. Okay, so let's see what we're going to do here. So let's see how we can apply this. Well, what acid are we using here? If you remember, cover up the H, that's your acetate ion, and so that's acetic acid. It says determine the hydrogen ion concentration and the pH of a 0.1 molar initial concentration, if you will, of the acetic acid, and they gave you the Ka. If they don't give you the Ka, you can always look it on your chart. So what's the first thing we have to do? Well, what's the major species that's going to produce the hydrogen ions? Is it the acetic acid or is it the water? Well, looking at here, look at your Ka value is much bigger than your Kw for water, which is 1 times 10 to the negative 14th, so that won't make too much difference. So my predominant species will be my acetic acid. So my acetic acid is in equilibrium with the H plus and the acetate ion, and then fill out the ice table. That shouldn't be anything new. So over here, you will fill out your Ka. What is the law of mass action? Hopefully this looks very familiar. Okay, so now it's a matter of plugging in the numbers. So what did we define H plus and the acetate ion? They're X. What did we define our acetic acid as? 0.1 minus X. So here I plugged in the values. But go back one more time. What do you remember about the X is small? Look at your Ka value, 10 to the negative fifth. So if you have a small Ka value, something in the terms of the negative fifth, what can I do here? I can cross out my X. So we can just take the X and go chink, chink. We don't even have to use it. So now what happens is our value, or our expression, notice how I just wiped out the minus X. Holy cow, our life gets so much easier, doesn't it? So what did we end up with? We end up with X squared is equal to, well, multiply both sides by 0.1, and we get 1.8 times 10 to the negative 6. And what does X then become? I had to scroll it down a little bit so I could have a little more room here. So I took the square root of both sides, and I get X equals 1.3 times 10 to the negative third. So just stop right here for a second. What should we do now once we found our X? Make sure you do your 5% rule. So what is 5% of 0.1? You get 0.005. What is this number is 0.0013. Is 0.005 greater than or less than, if you will, 0.0013? It's greater than. Our 5% rule works. So I didn't jot that down. You might want to put some kind of note in your notes here that you should be thinking of that. So what is, we're almost to the bottom of the list of rules. So what do we define our H plus value as? It's defined as our X. If you look right here, That's your X. So my X value, I don't have to multiply by 2. I don't have to subtract it from anything. They're not asking me for the equilibrium concentration of my acetic acid. They just want to know my H plus. So it's just plain old X. So whatever my answer over here was is my H plus value. And now to find the pH, take the negative log of my H plus concentration, and I got 2.89. Hopefully you did too. Let's see what the next problem holds. So it says the hypochlorite ion, if you remember what hypochlorite is, it's ClO negative, has a high affinity for protons, which means what? It's a much stronger base for the Cl minus. Remember, chloride is the conjugate base of a very, very strong acid, so it will not accept any of the protons. Hypochlorite will. And it forms the weakly acidic hypochlorous acid, and here's the Ka value. Ooh, look at that, -8. I'm already feeling pretty happy here. So it says calculate the H3O plus, which is the same thing as the H plus, and the pH of a 0.100 molar aqueous solution. So what do we do again? It seems like same thing that we just have done before. Here is our ice table, and I now need the law of mass action. So why don't you go ahead and write that down. That's what I got. And then go ahead and plug in your values. And now wait a minute. Hold on 1 second. What do we know? That Ka value is really, really small. So what does that mean I can do to this term? I can just cross it out. Okay, that made me feel pretty good right there. Hey, and that's equal to 3.5 times 10 to the -8th. That was the value they gave me right here. It's my Ka. So now multiply both sides by 0.1. I get 3.5 times 10 to the -9th, and I'll take the square root of both sides. And this is what I got. So that's my X, and not only is that my X, that is my H plus concentration. And so what's left is to find the pH, and it is the negative log of the 5.9 times 10 to the -5th, so pH is 4.22. Why don't you go ahead, account for the fact that the problems 20 and 23 each have 0.1 molar initial solutions of acid, but the pHs are very different. What is the difference? This is a pH of 4.22, and the other one was a 2 point something. It all has to do with Ka. So the weaker acid is going to give off fewer H plus ions, so the pH is going to be higher. In the previous problem, the Ka, if it's number 20, I think that was the HCl, has an infinite, it's a strong, strong acid, so its pH is going to be much, much lower. Why don't you go ahead and try problem number 24, set it up just like before, see what happens here. You might have to do the quadratic. Go for it. So go ahead and pause this and work this out and see how you do. Okay, welcome back. So I set up my ice table, and here it is. And I hate to say this, I kind of cheated where I did not do the law of mass action, but I have the next step right here. So I have the H plus and the NO2 minus right here. Here's my HNO2. And over here, I am not very happy because this is not times 10 to the -5th. Oh, very, very sad. So I do have to multiply both sides by the denominator, and then I do have to distribute. Okay, and then I did rearrange this to get in terms of y, the quadratic. So when I do this, and I'm using my quadratic solver, I did get x equals 0.0093 as the only root that would make sense. So next is, here is my H plus concentration, and my pH is 2.03. Okay. Problem number 25 is the same exact problem, however we have 0.0200 molar. So we have 0.020. It's a tenth more dilute than this one. How will our pH be changed? So let's see how the next one goes. Okay, so here this is. I left out a lot of the work, like the initial ice table, the same ice table as before. So why don't you go ahead, pause this, and then see how you do. Okay, this is what I got. So here's my, in a sense, my law of mass action. The only difference between this problem and problem A is the denominator right here. So I multiplied it both sides over here, and the only number that's going to be different is this term right here. This was a -5 on the previous page. This is a -6 on this one. So when I went here and I solved with my quadratic solver on my phone, it only gave me to the nearest 1,000th of the root, so 0.003. I don't have any more sig figs, and I guess if I really want to, I can, use my my calculator to come up with more better answer than 0.003. But for right now, this is fine. It will prove my point. So H plus is 0.003 if you go back and look at your original ice table, and so the pH is 2.52. So if you have the exact same acid but a more dilute initial concentration, your final result, your pH will go up. Why is that? Well, if you have less initial stuff to start with, you're going to make less H+. Less H+ means a higher pH. So what two things really will determine the pH of a solution is your Ka, the strength of your acid, and your initial concentration of that acid. And I think I just answered what's the effect of lowering the initial concentration? Your pH goes up. Okay, and then it says finding the pH of a weak acid in cases where the X is small approximation does not work. I didn't use it for before. I didn't even think I should with a -4. And so here, check this out. There is just no way, Jose, that this is going to work. So I gave you my famous German story here. Ich bin nicht fröhlich. You do have to use a quadratic. So I have already solved for this. Go ahead, you do the work, and my answer was 1.55. Okay, so let's see if you can get the same answer. If not, we can do it next time we meet. So I hope this helped. That's it for part 2, and we'll see you next time. Don't wait to be great.